Okay, welcome. It's a nice rainy day. I'll try to be engaging so that you don't fall asleep. It always seems like a sleepy, gray, dreary day outside, which is unusual because it was sunny when I woke up this morning. Not when I woke up, but 2 hours after I woke up. Okay, so today we are moving on to Unsteady Flow. And the homework that is assigned for that is just 3 problems, but don't let that fool you. It's actually a little bit more complicated. We're doing a lot of examples today with Unsteady Flow, so you'll see how it varies, how it differs from steady flow. There's additional components involved that we have to consider. And these problems can be very confusing as you read them. So make sure that you give the homework a lot of thorough thought, because there will be at least one unsteady flow problem on the exam, and knowing how to do it and how it differs from steady flow and being able to differentiate those types of problems when you read the problem statement is very important. So mentioning the exam, it's on Tuesday, so 1 week from today. Thursday will be a review session where I will go through lots of example problems, and I will expect you to help me with those problems, so come prepared to be volunteered to come up to the board. And then I'll have extended office hours on Tuesday and Thursday this week, so I'll be in my office till about 2:30, just so you can stop by, ask questions, receive help. Hopefully everybody has turned in their homework. Any more? Okay, bring it on up. That again, if you're struggling to complete the homework independently, then you really, really need to work on that, because the exam is not going to be concept questions. It will be homework style problems. So be mindful of that. So today we're venturing into unsteady flow, uncharted waters, and we'll talk about what that means for engineering problems. Yes? Have I ever failed you in getting it back by Thursday? Yes, you should have it back by the exam. You won't. This other homework isn't due until the day of the exam, so you can still use it to study. But again, it won't be graded, so you won't have that feedback on there. But yes, this homework I should have back to you on Thursday. Forbid, any unforeseen circumstances. That's my plan. Okay, so we talked about steady flow previously, and that most engineering devices operate under steady flow conditions. We talked about how we look at steady flow cases because that's the brunt of the operation time, but also because they're easier to analyze. So in steady flow, the properties of the control volume are not changing with time. You may have different property values at the inlet or at the outlet, but overall the system is steady. It's at equilibrium with its process, so the properties are not changing as the process proceeds. But during unsteady flow, the properties of the control volume will change with time, so we have to take that into account. However, we need to have some finite time period over which to analyze it. We can't just say, we're just going to find the unsteady flow conditions of this particular engineering device without saying we're studying it for a certain amount of time. Because if it's unsteady flow and the property values are changing, we need to take a snapshot at some point to figure out what is the time period that we care about. In many cases with unsteady flow, it's like from a start time until it reaches steady flow. That's usually what you're concerned about in engineering, or when you're at steady flow and then you turn off your system. What are the changes that happen as it ramps down? So the control volume is not necessarily fixed in size or shape, because the property values are generally changing and there may be a moving boundary. So with a piston cylinder device or with a balloon that's inflating, there are a lot of different conditions under which you would have unsteady flow and a changing control volume. So it's important to know how to analyze every type of situation. So you can probably see how throughout the semester we're building upon the information that we learned earlier and then making our problems, our systems, a little bit more complicated. So we're learning the skills that will be needed to do a thorough engineering analysis of any system. Similar to all of the other problems we've done up to this point, that we can perform a mass balance for the system. But in this case, we have the right-hand side of the equation, previously we assumed that the mass in was equal to the mass out. Well, now we have this change in the mass of the system. Okay, so the mass might be increasing, it might be decreasing, but we now have this change. Similarly, we can rewrite this equation as m in minus m out is equal to the final mass minus the initial mass. Or in other words, if you're looking at your system, you can determine how much mass you have at the end, and if you subtract off the initial value, you know how much mass entered or exited your system during that time period. You might also note that there's no dots over these. Okay, again, because we're analyzing it over a finite time period, the time factor is removed. Okay, so we're not looking at it at an instant in time where there's some flow rate. We're looking over a time interval, so we are looking at total mass and total energy changes as we analyze these systems. So the m dot and the q dots, the dots all disappear because time has been factored out. If we want to just talk about it for control volume, mi minus me, so that's the inlet and the exit. Sometimes this is also an O, mi minus mo, represent the inlet and the exit is equal to this m2 minus n1, or the initial and the final. Okay, again, it's very, very, very important to keep track of your subscripts. So whatever nomenclature you decide to employ in your problems, make sure that you stick with it throughout the problem. One thing I saw, a student came to me and was having a lot of trouble analyzing the heat exchanger problem on the homework, and he was getting so confused. And it was because he had, you know, like some system with 2 inlets and 2 exits, and he called them both 1, 2, and 1, 2. So when he's doing his problem, he had a mass 1, a mass 2, and an H1 and an H2, and he's like, but these are different values, and how come H2 doesn't equal to H2? And it was because of his labeling on the diagram that he got himself confused. So be very careful about that. If it's an inlet and an exit, that's different than a 1 and a 2 if that's initial and final. Yes, question?
I have a question about that kind of system. What's it really do? I was kind of confused about it on homework.
What does a heat exchanger do?
Yeah, like is it just cooling down that pipe?
Yeah, so heat exchangers are used anytime that you want to remove heat or add heat to a system. So a prime example of that would be like the radiator in your car, that it's cooling the engine by passing fluid over it, and then this radiator takes that hot fluid and allows air to pass through it to remove that heat. So in engineering design and systems, the greatest problem that engineers face as far as constraints is usually heat removal. So electronics can only get so small before there's too much heat that can't be removed in that tiny amount of space to allow these electronics to operate at more powerful conditions. So heat exchangers are very widely used for that, even on a nanoscale. So it's, are you a mechanical engineer, civil engineer? Yeah, so as you proceed forth in thermo and in heat transfer, you'll learn a lot more about heat exchangers and how important they are for any kind of engineering system. And you can see them everywhere. I mean, they're on refrigerators, they're on computers, they're on everything. And so sometimes it's liquid flowing through them, but a lot of times it's air. Okay. Any other questions? Okay. We do make the assumption of uniform flow. So because our property values might be changing with time, we assume that it's uniform across the inlet and the exit, and that that if we have some big, large system, we're assuming that it's uniform across the system. So there won't be significant temperature gradients or property changes, density changes, things like that across the control volume. So we have to make that uniform flow assumption just so that we can analyze it using traditional methods. Otherwise, we have to do a numerical model or a computer simulation to figure out exactly what's going on in the system. And then if the properties don't change with time or position, then the average value is taken and the property is treated as a constant. So we just say that it's some constant average value at the inlet or the exit. Sorry, if they do change with time or position, we take a constant value, not if they do not. If they don't change with time or position, then there's really nothing to analyze. So we've talked about mass balance. This is the energy balance equation, and very similar to what we've seen before. Again, this right-hand side of the equation previously was 0. So now we have this M2E2 minus M1E1 of the system, or the change in energy of the system. So for a uniform flow, this is the general form where Q in plus work in plus the sum of the flow work in, and the flow work includes this enthalpy term plus the kinetic energy plus the potential energy, minus Q out, work out, and then the sum of the flow work out. And then we're setting it equal to this M2E2 minus M1E1. And again, remember, this is the initial state, this M1E1, and M2E2 is the final state. We're no longer looking at it as the inlet and the exit. That's on this side of the equation. So the inlets and the exits are on the left-hand side of the equation, and then the initial and the final state are on the right-hand side of the equation. So it's so important to know that that's physically what that represents, and that your subscripts should make sense to you when you write them down. So if there's just single inlet, single outlet, then this sum term can be, where'd my laser go? This summation term can be, instead of a summation, it's just a single inlet. And then if we ignore kinetic and potential energies, then this theta term just turns into H. So this is another way of writing the exact same equation. You'll see it written in many different ways. It's all the same equation. It just depends on how you group your terms and what side of the equal sign you want to put them on. Okay, so be very careful that as you're moving things around that you keep the proper signs. So if you change something to the other side of the equal sign, you have to change the sign of it. So a negative turns into a positive, things like that. That's one of the most common mistakes I see on homeworks or on exams, is that you're moving things around and you're not being very careful about the signs. So let's do an example. And this is kind of an interesting example because we're going to look at it two different ways. We're going to look at it as an unsteady flow, open system, and then we're going to look at it as a closed system with boundary work. So we can imagine that we have a set amount of mass that comes into this system over some finite time period, that we can either look at it as an unsteady flow system, or we can say, okay, what if there's this imaginary piston cylinder device? And now instead of looking at it as unsteady flow, I look at it as a closed system where this is the boundary of my system, and all of this mass eventually moves into this smaller volume. Okay, so that's another way of looking at it. It's kind of interesting to see that they both end up with the same answer, which they should because the energy balance says that they should. So let's look at this problem, and using our 5-step process, which is no longer written up here, but hopefully you remember the steps, what do we do? Identify the system. Okay, so we are first going to look at it as an open system, unsteady flow. Okay, so we've identified it. There's a nice picture up there. What's the second step? Okay, so list our assumptions. We want to assume uniform flow, that kinetic and potential energies are negligible, and it's insulated, so we're also going to assume that it's adiabatic. So that's another good assumption that we can make. Okay, so I'll write these down. ID the system, list assumptions. What's step 3? Find properties. Step 4. Okay, apply energy or mass balance. And then step 5, solve for unknowns, right? Okay, so we've identified the system, we've listed our assumptions, we need to find some property values. What fluid are we dealing with here? Steam. Okay, so steam at 1 megapascal and 300 degrees Celsius, what is that? It's a superheated vapor. So what property values do you think we might need for this problem? Say that again. Okay, specific volume and enthalpy, and we're probably going to need internal energy too, because if you remember from the previous slide, that shows up in that equation too. We have enthalpy, we have internal energy, and specific volume is often needed to find the mass. So let's just look up all those property values. And I haven't put any subscripts on these yet, so we're going to talk about that in a minute. Okay, so what is the properties of steam at 300 Celsius and 1 megapascal? .25799 meters cubed per kilogram. That's the specific volume. 2793.7 kilojoules per kilogram. That's the internal energy. 3051.6 kilojoules per kilogram is the enthalpy. Okay, now I don't have any subscripts on this. So those property values at 1 megapascal and 300 degrees Celsius, what are they related to? As far as in our energy balance, is it the initial state? Is it the final state? Is it what's coming in? Is it what's going out? What is it? It's what's coming in, right? That's the supply line. So we're going to call those U sub I, H sub I, and V sub I. Okay, so it's very important when you identify property values that you figure out what they relate to in the system. Okay, so in this problem, we're trying to determine the final temperature of the tank. Initially, the tank is evacuated, so there's no initial property values. So initially the tank is evacuated, there's no property values. The mass is 0, so there's nothing in the tank, right? So we're looking at the initial state and the final state, but we're also looking at what's coming in. So this U sub I is the inlet, so maybe we call it in instead of I, just so we don't think it's initial. But what is our system? Just the tank, right? Not the supply line. So initially, we can look at the initial property values. We can talk about that. So the mass is 0. The pressure is what? Is it? 0. An evacuated tank will have 0 mass and 0 pressure. Okay? So the final state, so we can call initial state 1 and the final state 2. What's the property values of the final state? Okay, we know the pressure, P2, is 1 megapascal. We don't know anything else yet. We need to find the temperature, we need to find the mass, and figure out what are our property values of the final state.
So the initial is before the valve?
Right. Right, so again, we're looking at this finite time period. So we set the initial conditions as the tank before the valve is opened, and then the final condition is when the pressure reaches 1 megapascal, then the valve is closed. Okay, so we open the valve and we close the valve. There's this finite event occurring over which we analyze how the system changes and look at how much mass enters the system and what the property values are. Does that make sense? Okay, so again, these problems can be very confusing if you're not sure what is initial, what's coming in, you have to really, really carefully read the problem and set it up. Okay, so we've found all the properties that we can for now. Step 4, we need to apply our energy and our mass balance. So the energy balance is similar to that for an open system steady flow, but remember, we're not analyzing it as a rate. We're looking at a finite time period, so it's just total amounts. So we have Q in minus Q out plus work in minus work out plus M in H in minus M out H out is equal to M2 U2 minus M1 U1. And then we do the same thing, okay? Let's look at these property values and figure out if there's anything that we can get rid of. So do we have any Q in or Q out? No, it's insulated, work in, work out. Nope. Mass in, mass out. Nope. Do we have a final state? An M2? Do we have an M1? Do we have an M1? No, it's initially evacuated, right? M1 is 0, so we have no M1. So from all of this, we have M in H in is equal to M2 U2, right? Okay, do we know H in? Yes. Do we know U2? No. Do we know M1 or M in? Do we know M2? No. Okay, so we have a couple of unknowns in this state. We can now perform a mass balance that we have M in minus M out is equal to M2 minus M1. So again, do we have mass coming in? Do we have mass going out? Do we have mass at the final state? Mass at the initial state? Okay, so M in is equal to M2. Which means that M in is equal to M2 here in this equation. This can reduce down to H in is equal to U2. Or in other words, U2 is equal to H in. So we found this here, right? We can write down U2 is equal to 3051.6 kilojoules per kilogram. Okay, so ultimately for this problem, we're trying to determine the final temperature of the steam in the tank. We know that the final pressure is 1 megapascal, and then we just determined that the final internal energy will be this 3051.6 kilojoules per kilogram. So what do we need to do to find the final temperature? Yeah, so we go back to the table and we say, okay, at 1 megapascal and that specific volume, let me figure out what my state is. So the first place I usually go is the saturated liquid tables and see if I'm above or below the values there. So in table A5 at a pressure of 1 megapascal, right? 1 megapascal is 1,000 kilopascals. Okay. So our U value for U sub G is 2582.8. Are we above that? Yeah, we're above that. So we have to go to the superheated table at 1 megapascal. And we look for the point where our U2, or our U value, is 3051.6. And we look at the table and we find it somewhere in between 400 and 500 degrees Celsius. Because 400 is 2957.9 kilojoules per kilogram. So at 400 degrees Celsius, U is 2957.9. And at 500 degrees Celsius, U is 3125 kilojoules per kilogram. So by interpolation, using these temperatures and these internal energies, and then the one we already know, we can find T2 is equal to 456.1 degrees Celsius by interpolation. So again, we're using these values and that value to figure that out. So it's good, it'll be a good practice for you to go and make sure you know how to interpolate to find that T value. Okay, any questions on that? Let's look at this another way. So you remember I said that we can also analyze it as a closed system where all of that volume of mass is then moved into the initially evacuated system. So we're looking at the entire thing as our system. So if it's a closed system, the energy balance is Q in minus Q out plus work in minus work out is equal to M times U2 minus U1. So we're saying that mass is just we're relocating it into the chamber itself using some piston. So again, Q in and Q out are 0. But now, instead of having 0 work interactions, we have a work in, which is our boundary work, is equal to M times U2 minus U1. So this work in we can rewrite as P V in, let's see, P times the volume that we move in. So we're changing this volume and putting it into, or the change in volume of that, not being very clear, is equal to M, let's see, P times V times the mass is equal to M times U2 minus U1. So then we can rearrange this if the mass times PV plus this U1 term, so we'll get rid of the mass. We have PV1 is equal to U2 minus U1. U2 is equal to PV1 plus U1, which is the same as H. So we found the same answer, just a different way. So we're looking at that volume of that piece of mass that we're putting into the system, if it's some known quantity over this time period, that we'll figure out the same thing, that our U2 is equal to H1 for this particular case. Okay, any questions on that? And I don't expect you to analyze unsteady flow systems using them as a closed system. Like, I'm not going to say do that on an exam because it is a little bit trickier to think about. But being able to analyze it this way is important, and knowing that flow work is equivalent to boundary work in a closed system. Okay, so let's do another example. As I mentioned, we're doing a lot of examples today. This time we have a tank that has a liquid vapor mixture in it. Can I erase this? Is everybody done here? Of R134A. So can someone read that property statement for me, or the problem statement for me? Who's got a nice lap? Chris, thank you. Yeah, read it all. Okay. So we've identified our system as an unsteady flow system. There's a tank, there's liquid vapor in it, there's a valve at the bottom where the liquid can flow out. And this, by the way, would be a common thing that you would encounter, like in refrigerant systems. Sometimes they're drawing off the liquid so that they can revaporize it. That often you'll have a valve in the bottom so you can pull off the liquid, and then a sensor that tells you when vapor starts coming out, and that's used to be more efficient so that you're not trying to, again, pump vapor. So the volume is known. Let's start by identifying the system, listing assumptions that it's uniform flow, constant pressure, because there's a liquid vapor mixture in there, and then the changes in kinetic and potential energy are negligible. Okay, so let's look at our state 1 initial. What are the conditions on it? So P1 is 800 kilopascals. V1 is 0.12 meters cubed. What else? We have to be careful about that because it's 25% of the volume, not 25% of the mass. So, 25% volume is liquid. 75% is vapor. Okay, which is not the same as quality, because with quality it's 25% of the mass would be liquid, and volume and mass aren't directly correlated in that way. Okay, but that we do need to know some of that information to find property values. Okay, so the initial state, it's a liquid vapor mixture. We have to find some combination of property values possibly. What about our final state? Okay, the pressure is constant. We're just drawing off the liquid. What else? What's that? The quality is 1. Okay, so this we do know because all of everything in the tank will be vapor. So that fixes our state at the final condition, right? It's all vapor and the quality is 1. All right, what do we know about the outlet? What's coming out of the system? Okay, water. What's the state of it? Liquid. Okay, so liquid water. What else do we know? Okay, yes, but that's looking at initial. We're just looking at what's coming out. So imagine we know nothing else about the rest of the system other than this water that's coming out. What is its pressure? What is its temperature? What is it? Refrigerant, liquid refrigerant. Yeah, it's not water. Come on, Sam. No, just kidding. Okay, I thought it was water too. Liquid. So the same applies whether it's refrigerant, whether it's water. We use the same process. So the pressure at the outlet is going to be 800 kilopascals because we're directly drawing from that water that's in the tank, right? It's at 800 kilopascals. It's going to be coming out at 800 kilopascals. And the quality of it is going to be 0. Okay, so our final state, we're going to use the gas properties of this R134A, and then our outlet is going to be the liquid properties of R134A, and our initial state is going to be some mix between the two. Okay, so let's go to table A12. For R134A. So table A12, let's look up V sub F, V sub G, H sub F, H sub G, U sub F, and U sub G. And for time constraints, I'll just write those down. Correct me if any of these are wrong. I feel like I should be singing this song so the people who are watching this video don't get bored, if anybody ever watches. Okay, so V sub F is 0.0008458 meters cubed per kilogram. V sub G is 0.025621 meters cubed per kilogram. H sub F is 95.47 kilojoules per kilogram. H sub G is 267.29 kilojoules per kilogram. U sub F is 94.79 kilojoules per kilogram. Yes. Yes. Is there something wrong? Okay. They must have changed the table slightly. Now, I'm going to keep these values just because that's what I calculated everything with. I have noticed actually from the 6th edition to the 8th edition there's slight changes to the tables. Yeah, it happens in a couple of other problems where I've done it using 6th edition. There was a student who emailed me about that and I went and looked and the tables are just slightly different. But since I've already worked this problem using these numbers, we'll keep it. So listeners, if your values are slightly different, that's why. Okay, so let's correlate these to our initial, final, and outlet states. So V sub G, that's going to be V2, right? V sub F is going to be V sub out. H sub F is going to be H sub 2. H sub G, no. Yeah, H sub F is H out. HG is H2. V sub F is V fluid out. No, that's a U. U out. And U sub G is U2. And then U1 is going to be somewhere in between those. Okay. Which we have to figure out later. Okay, so in our question, we are trying to determine the total heat transfer for this process. So a good way to figure that out would be to do an energy balance, right? And I'm going to move over to this side of the board. Okay, so we've found our property values. We've looked up what we can. We're going to apply our natural laws. So Q in minus Q out plus work in minus work out plus M in H in minus M out H out is equal to M2 U2 minus M1 U1. Okay, so let's start canceling things out. Do we have a Q in or a Q out? Q in. Okay, the picture tells us that. If we didn't know, we weren't sure, is heat going to enter, is it going to leave? You know, if we're not sure about that. Whatever one we choose, if we end up with a negative value at the end, then we know we chose the wrong one and we just say, okay, it's a negative Q in, so it's actually a Q out, something like that. Do we have any work interactions? Do we have mass coming in? Do we have mass going out? Do we have initial mass and final mass? Okay, so those stay. So we have Q in minus M out H out is equal to M2 U2 minus M1 U1. We don't know Q in, that's what we're solving for. Do we know M out? How much mass leaves? Not yet. We'll have to solve for that. Do we know H out? Yes, we looked that up. Do we know M2? No. Do we know U2? Do we know M1? No, we'll have to figure that out, right? And U1? We don't know that either. We have to figure that out. Okay, so let's start figuring out some of these unknowns so we can solve for Q in. let's first tackle the mass. We don't know the quality of this system, but we do know the volume and how much of that volume is in specific states. So we know that 25% of the volume is liquid. So if we want to find the mass of the liquid, we can do that. So mass of the, we'll call it liquid initially, mass of the liquid at state 1, is going to be equal to the volume of the liquid at state 1 divided by V sub F. So 25%, 0.25 of 0.12 meters cubed divided by V sub F, which is 0.0008458 meters cubed per kilogram. So we find that our mass of our liquid initially is 35.47 kilograms. And then the mass of the vapor portion at state 1, again, is the volume of the vapor at state 1 divided by V sub G. So it's 0.75 times this 0.12 meters cubed, and then divide by V sub G, which is 0.025621 meters cubed per kilogram. So we find that is 3.51 kilograms. So 35 kilograms of water, 3.51 kilograms of our vapor. We could use that to calculate the quality if we wanted. X is equal to 3.51 divided by 3.51 plus 35.47 kilograms. So we find our quality to be 0.09 at the initial state. And it turns out we won't actually use that, but sometimes you will. So the total mass at our initial state, M total, which is equal to this M1, is just this 35.47 plus 3.51, which is 38.98 kilograms. Okay, so now we know M1. We need to figure out M2 and M out. M2 is a little bit easier to figure out because we can just look at the entire volume and then the specific volume of the vapor. So I'll do it over here. M2 is equal to the total volume divided by V sub G. So now instead of only 75% of it being vapor, 100% of it is vapor. So it's 0.12 meters cubed divided by 0.025621 meters cubed per kilogram. So M2 is equal to 4.68 kilograms. So we have M1, we have M2. We can perform a mass balance to figure out how much mass left the system to find M out. So M in minus M out is equal to M2 minus M1. We don't have any mass coming in, so M out is equal to M1 minus M2, or in other words, 38.98 minus 4.68, which gives us some number that I didn't calculate. So somebody calculate that real quick. So I just put it in symbolically when I solved it. Okay, so now we know M2, we know M out, we know U2, right? And U1 we don't know, but we know how to figure it out. And we know H out. Right. Okay, so we can use x1 to find u1, or we can say that u1 is equal to the mass of the liquid times u sub f plus the mass of the vapor times u sub g. Or we can use the quality and calculate u1. I'm going to move over here. I never use this board. So Qn is equal to M2U2 minus M1U1 plus M out H out. So if we start plugging in the numbers for that, we have 4.68 kilograms times U2, which is the U sub G from over there, 246.79, is that right? Kilojoules per kilogram, minus M1, which is 38.98 kilograms, times U1, which is, sorry, this is M1U1. I got to break it up. So M1U1 is the 3.51 kilograms multiplied by 246.79 kilojoules per kilogram plus 35.47 kilograms times 94.79 kilojoules per kilogram is our M1U1 term. Plus this mass going out, which is M1 minus M2, which we didn't solve for. What was it? 34.3 kilograms plus 34.3 kilograms times this H out, which is the H sub F, which is 95.47 kilojoules per kilogram. So if we plug in all those numbers, we find Qn is equal to 201.2 kilojoules. Okay, so we have M1, but we don't have U1. So we can either use the quality and solve for U1, which we can do here. So U1 is equal to U sub F plus X U F G, which I did it this way, so I didn't have these numbers, but it would be 94.79 kilojoules per kilogram plus this 0.09 times UFG, which is the 246.79 minus 94.79. So we'd get some number for U1. But I just did everything all symbolically, and then I ended up putting the numbers that way. You'll get the same answer. There's two different ways to skin a cat. Okay, any questions on that? So even I was getting confused, and I had the paper in front of me on this particular one. When there's a liquid-vapor mixture in the tank, it makes things significantly more complicated because you have the fluid state, the gas state, the inlet state, the outlet state. You have to be very careful to keep track of everything. So let's do another one where we have a liquid vapor, and this time we have mass flowing into the system. So again, it's R134A, this time at 8 degrees Celsius. So the tank is full of R134A at 8 degrees Celsius, and the quality is 70%, or 0.7. The tank is connected to a supply line with R134A at 1 megapascal and 100 degrees Celsius. So we're going to approach this problem in a similar way. The valve is open, the refrigerant is allowed to enter the tank. When the pressure in the tank reaches 800 kilopascals, then the refrigerant in the tank exists in the saturated vapor state only, and the valve is closed. So let's go through again, and we have this nice picture up there. We're assuming kinetic potential energies are negligible, that there's uniform flow. We don't know it for certain, but we assume that Q is going to be flowing into the tank. And if we make an incorrect assumption on that, our negative sign at the end will tell us we need to go back and look at things. So we have a state 1 initial, a state 2 final, and instead of having an outlet, now we have an inlet condition. Okay, so state 1, what is our initial condition of this R134A? T1 is 8 degrees Celsius, and our quality is 0.7. What's our final state? Okay, it's saturated vapor, so the quality is equal to 1. So our quality is 1 and our pressure is 800 kilopascals. Okay, so those states are fixed. We'll be able to look up all the property values at the initial and the final state. What about our inlet conditions? What's coming in? So 1 megapascal and 100 degrees Celsius. So this is Pn, Tn, this is X2, P2, and this is T1 and X1. Okay, so let's look up some of the property values. Actually, before we do that, let's do the energy balance to figure out what property values we actually need, so we don't waste time getting ones we don't need. So Q in minus Q out plus work in minus work out plus M in H in minus M out H out is equal to M2 U2 minus M1 U1. Okay, do we have heat transfer in or out? In. We're going to assume it's in, so there's no Q out. Is there a work in? Work out? Is there an M in? M out? Is there an M2? Do we have, will there be mass in the tank at the final state? Yeah. What about initially? Is there mass in the tank? Yeah. So M2 and M1 are both there. So this is Q in plus M in H in is equal to M2 U2 minus M1 U1. So we need to figure out H in, U2, U1. We're probably also going to need V to solve for the mass. So we'll look up the specific volume and internal energies at the initial and final state, and then the specific volume, or actually probably just the enthalpy at the inlet conditions. Okay, so X1 equals 0.7. What is U1? U sub F plus X times UFG. So at 8 degrees Celsius, we can look up those property values, and we find that our U1 is equal to 62.39 plus 0.7 times 234.58 minus 62.39 kilojoules per kilogram. So we find U1 is 182.92 kilojoules per kilogram. We can do the same thing for V1. I'm not going to write all the numbers out, but we find V1 is V sub F plus X, VFG. The number on that is the final 0.03717 meters cubed per kilogram. Okay, so we have U1, we have V1, we need U2 at 800 kilopascals and the quality equal to 1. We use our U sub G values. U sub G So we find that U2 is equal to 246.79 kilojoules per kilogram. And then if we look at the conditions of our inlet, we find our specific volume is 0.027552 meters cubed per kilogram. And our enthalpy in is 335.06 kilojoules per kilogram. That's an H. Okay, so we've looked up our initial, final, and inlet property values. I'm just going to erase this because it's in the way. So U1 is here, V1 is there. Okay, so we need to solve for, let's see, we have U2, we have U1, we have Hn. We need to solve for the masses in order to solve for the everything else. Okay. All right, so part A, determine the final temperature. If we know that it's a saturated vapor at 800 kilopascals, then we can just look at the table and find that T2 is the saturation temperature at that, is Tsat at 800 kilopascals, which is equal to 31.31 degrees Celsius. So part B, we need to figure out the mass of the refrigerant, but in order to do that, we need M1 and M2. So M1 is equal to the volume over V1, and we found V1. So our total volume is 0.2 meters cubed divided by our specific volume, which is 0.03717 meters cubed per kilogram. So we find M1 is 5.38 kilograms. M2 is equal to the volume over V2, which is the 0.2 meters cubed, divided by 0.025621 meters cubed per kilogram. So V2 is 7.81 kilograms, which means the amount of mass coming in, if we perform our mass balance, mass in minus mass out, is equal to M2 minus M1. So mass in is equal to M2 minus M1, or 7.81 kilograms minus 5.38 kilograms. Oops. When? We looked, oh, well, okay, so we looked it up. V2 is V sub G at that temperature, and it was 0.025621 meters cubed per kilogram. Yeah, so it's just the V sub G value at this state 2. I didn't write it down, I'm sorry. So this comes from table A12. This one is table A13. Okay, so we find our mass is 2.43 kilograms, is how much mass entered our tank. Then we can solve for Q in is equal to M2 U2 minus M1 U1 minus M in H in. So it's 7.81 kilograms times 246.79 kilojoules per kilogram minus 5.38 kilograms times 182.92 kilojoules per kilogram minus 2.43 kilograms times 335.06 kilojoules per kilogram. So we find our Q in is equal to 129.12 kilojoules. Okay. So prior to now, all of our boundaries have been fixed except for the one problem where we assumed it was a closed system with a moving boundary. But let's look at how it changes when our boundaries are moving. So it just adds another layer of complication in some ways. But again, we follow the same procedures. So in this case, we have helium filling a balloon. The balloon initially contains 65 meters cubed of helium at 100 kilopascals and 22 Celsius. The balloon is connected by a valve to a large reservoir that contains helium at 25 Celsius and 150 kilopascals. Now the valve's opened and helium is allowed to enter the balloon until pressure equilibrium is established with the supply line. The material of the balloon is such that the volume increases linearly with pressure. If no heat transfer takes place during this process, determine the final temperature in the balloon. Okay, so we can make some assumptions. We're assuming it's uniform flow and that we're not worried about kinetic or potential energies. We can also assume it's an ideal gas because helium can be considered an ideal gas. And then they told us to assume that no heat transfer takes place, so it's adiabatic, and that our volume is increasing linearly with pressure, so we don't have to worry about the forces of the balloon changing the pressure and things like that. So we've got a nice picture up there. Let's start with our properties. So we have some things labeled on there. Let's talk about state 1, which is our initial. State 2, which is our final, and our inlet conditions. Okay, so what do we have at state 1? So T1 is 100 kilopascals. T1 is 22 degrees Celsius. And then do we know anything else? Okay, V1, 65 meters cubed. Okay. What about our final state? What do we know? Okay, so what is the pressure going to be? Okay, what is that value? So P2 is going to be at equilibrium with the supply line, so it will be 150 kilopascals. Do we know anything else about state 2? We don't know T2. We're asked to solve that, final temperature. We don't know necessarily the volume, but we do know that the volume is increasing linearly. Okay, what do we know about the inlet? Okay, so 25 degrees Celsius is T in, and P in is 150 kilopascals. Man, it's raining hard out there. Okay, do we know any other information, or do we have our initial, final, and our inlet conditions? That's all we know about them so far. Okay, so, but we do know this is an ideal gas, and we do know that it's uniform flow and the pressure increases linearly. Okay, so if we perform our conservation of energy, Q in minus Q out plus work in minus work out plus M in H in minus M out H out is equal to M2U2 minus M1U1. Okay, do we have any heat transfer? Adiabatic. Okay, do we have any work interactions? Boundary work. Okay, so there's no work in, but there is boundary work out. What about our, do we have mass coming in? Do we have mass going out? No. Do we have initial mass and final mass? Yes. Okay. So we will have negative work out plus M in H in is equal to M2U2 minus M1U1. Okay, do we know our initial mass? Oh no. Do we know how much mass comes in? No. Do we know our initial mass, M1? No, but we can find it because we know the ideal gas law. And we know that the volume increases linearly with pressure. So those two things are going to allow us to find our M1 and our M2. Okay, so for M1, PV is equal to MRT. So M1 is equal to P1V1 over RT1. So 100 kilopascals. Volume 1 is 65 meters cubed. R for helium is 2.0769 kilopascals times meter cubed per kilogram Kelvin. It's a G, kg. And then our temperature is 22 Celsius, but we have to convert to Kelvin, so 22 plus 273 Kelvin is 295. Solving for the mass, this gives us 10.61 kilograms. So initially there's 10.61 kilograms in the balloon. So we don't know the total volume at the final state, but we know that it's increasing linearly with pressure. So P2 over P1 should be equal to V2 over V1. Okay, V2 is equal to P2 over P1 times V1. Yeah, so V2 is 97.5 meters cubed. We don't know T2, so we can't solve for M2 quite yet. There's 2 pages to this problem. Okay, so we don't know M2. We know M1. We can figure out U1 because it's for an ideal gas, it's a property or a function of temperature, and we have ways of finding that with C sub P. We know H in we can find because we know the temperature coming in. But right now we don't know the temperature of the second state, and we don't know the mass of the second state. So we need more information to find those values. Once we find the temperature of the final state, we can solve for the mass or vice versa. So we have to find one or the other. So we got to do a lot of tricky work in order to do that. But we know the relationships for ideal gas, and we also know some things about boundary work when it's a linear process. So this is similar to when we have a piston cylinder device where the pressure and the volume are changing linearly. What did we do in those cases with the piston cylinder device to figure out the boundary work? We drew a picture, right? So the pressure and the volume, we can draw a picture. So we have 100 kilopascals and 150 kilopascals. But the boundary work is going to be the area under this curve, so 65 meters cubed and 97.5 meters cubed. And we can calculate the boundary work, if we just find the area of that, will be 4062.5 kilojoules. So now we have this equation where we know the boundary work, and we know U2, or no, we know U1, we know M1, we know M in and H in, but we don't know M2 and U2, but they're both dependent on the temperature, so we're going to write everything in terms of temperature. So M2 is equal to P2 V2 over R T2. U2 is equal to C sub V times T2. U1 is equal to C sub V times T1. H in is equal to C sub P times T in. So if we put all of these into our original equation, where we already solved for the boundary work, we get our negative boundary work, plus, and then also the fact that M in is equal to M2 minus M1. Sorry. I'm going to write this symbolic equation for this. So the negative boundary work plus M2 minus M1 H in equals M2 U2 minus M1 U1. So if we start putting everything in there symbolically, this negative boundary work, which we already found, plus M2, which is P2 V2 over R T2, minus M1, which we know the number for, times H in, which is C sub P T in, is equal to M2, which again is this P2 V2 over R T2, times U2, which is C sub V times T2, minus M1 U1. So M1 times C sub V T1. So the T2 here cancels out. We're left with this 1 T2 in our equation. So if we solve for T2, then we get T2 is equal to 333.55 K. Without going through all the numbers for that for lack of time. Okay, so just briefly, there was another example we didn't get to, but this is similar, where you're using boundary work. It's a little less complicated than that first example, so maybe you can try to solve this one on your own. It's the same as problem 130 in your book, and the answers are given there, but it's another good example using ideal gas and changing boundaries for the system. So if you have questions, email me, come visit office hours. The exam, we'll review that on Thursday, so all these slides are in there, but we'll talk about it again on Thursday because we're out of time, and get working on it.